Hello everyone. Welcome to a very brand new show of Think Again Lab, that is WebCamp. We are going to do this for every Sunday, 3 hours free session on different state of the art technologies, so that all the students of engineering, all the school students who is having interest in different kind of technologies, they can actually get a overview of different technologies, how these technologies works, and how they can start with these things. They can ask direct live questions. Those questions will be featured. And the most interesting part of this show is this is one of the first kind of a show where we are offering live scholarships, right? So if we will ask few questions regarding the thing we are going to teach today, that is PCB design and schematic designs, right? And those people who can answer those questions will get up to maximum 100% scholarships. All for all the questions they will get 10% scholarship, and we are having like 10 questions. So if one person is answering all the 10 questions, they will get a 100% scholarship. 100% scholarship for a paid 3-day masterclass web workshop for the same topic, the PCB design and schematic designs. So I hope everybody will enjoy through this session, because we are not only going to talk about it, we are going to actually show you how to build PCBs, how to design the PCBs, and why actually we need to design the PCB. So the thing is, most of the college projects, most of the college hardware projects never become products in most of the cases. The reason behind it, they used to do the projects on Vero board, breadboard, but they are lacking in the knowledge of how to convert those prototyping things into a proper format of PCB. So PCB is nothing but a board. It's a printed circuit board, right? So the circuit board is a circuit where the electron is flowing. We are connecting all the components so that we can create a proper channel for electrons to go from one component to another component from the sources, and again get back to the sources through the ground, right? Now if we are actually building this thing on a rigid body or a flexible thing, so that we can actually use it in professional products. So if you open your mobile phone, laptops, computers, you can see there are green color or blue color or black color boards, right? Or if you are working with small robotics things or this kind of things, you can see that we use Arduino and all those kind of stuff. Electronics, the implementation of electronical circuits is PCB. So if you really want to build a product out of your projects, this is one of the biggest essential thing that you need to focus on, right? And today Anirban Dotto, he's the robotics head and space tech head of Think Again Lab, is going to describe you what are different types of PCBs, which kind of components we actually use, and how we actually can create schematics and convert them into the PCBs, right? So be very aware, because we are going to give several codes for scholarship for our paid session that's going to happen a few weeks later, right? But you can actually register right now, because those coupon codes, those scholarship codes only applicable during this session, during this 3 hours, right? So be very attentive and try to gain as much as possible knowledge, as well as try to gain as much as possible scholarships. So thank you so much everybody for joining us. We are starting the show, and let us know if you have any preferable technology for which we can organize this kind of shows in later on weeks, right? So hold on with us, and thank you so much, and comment your answers, your queries, right? So the way we do webinars in Zoom platform or this kind of webinar platforms, we are actually asking you to interact with us in the same manner, right? So if you are having any questions, maybe it's in Bengali, Hindi, English, just comment it down. We are getting comments from all the platforms. So right now we are actually streaming it in Facebook group and YouTube, so you can watch it from anywhere and comment there. We will flash your comments on the screen, and the expert will answer your questions. And the questions we are asking you, answer those questions as well in the comment section, and the fastest winner will be given scholarship codes for the registration of the final event, right? And suppose you have answered 3 right questions, so you will get 30% scholarship. If you have answered 10 right questions, you will get 100% scholarship, right? So that's how this thing will happen. So be very attentive just ask all the questions that you feel that will be helpful for you to understand PCB. So be very much interactive with us, and all the best. Thank you so much. I am inviting Anirban to take the stage.
Hi everyone, my name is Anirban Datta. I am right now the Robotics and Space Tech Head of Thinking in Lab. So let's get started with this workshop. So today we are going to learn Introduction to PCB Designing. So basically, what is a PCB? A PCB is an acronym for Printed Circuit Boards. So let's dive in and learn a little bit about PCBs. So a printed circuit board is it's a mechanical support for your circuit, because if you think about it, wires are just flexible things that does not really support your circuit mechanically in any way. So PCBs are built on solid structures, usually it's fiberglass, so that it can provide electrical as well as mechanical support to your projects. So PCBs usually come at the end of the process. So you have completed your projects and you're ready to make a product out of it, and then you go ahead and build a PCB out of it, because PCBs are a lot more reliable than any other type of prototyping. So let's get into a little bit about the history of PCBs. So PCB was originally invented by Paul Ellister, like in 1936. So he built the first PCB for building a simplified radio. So that time radio was in craze, and before this invention, wires were simply tacked together and soldered together to build a circuit. But he decided that no, we can put all of these things and on a like a board-like structure, and then we can provide more support to the like the radio, and that will last longer. So he named those things printed wiring boards, or PWBs. And then the technology was released to the public in 1948, 1 year after our independence, and then this thing slowly evolved into something that we know today as PCB. So, since we are all here for the PCB development and design, so let's learn a bit about PCB development. The first stage of PCB development, as I said, is getting started with your projects. So we usually start our projects with a breadboard. So a breadboard is basically a rapid prototyping tool where you can change anything and everything in your project. So you have not decided what sensor to use, you have not decided what microcontrollers to use. So that's the time when you use a breadboard. So a breadboard usually looks like this. This is a full-size breadboard. It can be smaller, like a half breadboard, or a very small micro breadboard, which is around this small. But the full-size breadboard looks like this. And this breadboard has a very interesting interconnected structures, which means that if you connect one point on this breadboard, you can have extensions of that point, multiple points branching out from that point, all electrically shorted. So let's see that interesting structure I am talking about. So this is the structure of a breadboard. As you guys can see, the whole top part of the breadboard is connected with a small brick in the between, right there in the middle. So in case of our breadboard as well, if I show you guys will be able to see that there is a patch wire I have connected from this side to this side. This is because this whole side is connected, that whole side is connected, but there is a break in between. Like for applications where it's more complicated and you need to make a more like complicated wiring structure for that purpose. But for simple wiring and stuff like that, you can just short these things out, and now you have two full lines going in horizontal direction. Now for the center part of the breadboard, this part, there and there, these two parts, we have vertical connections. So this top and bottom part, these are horizontally connected, and this part and this vertical part, these two, the big sections, are vertically connected, which means that they are connected in a vertical fashion, and these horizontal connections are not shorted in the vertical section. So with this knowledge, you can now build your own circuits. Like say you're building an LED circuit. So you would use this breadboard and then something we call jumpers like this. So this would help you to go say from point A, which is right here, to point B, which is say right here. And now you have connected these two with a wire. So I'm not removing this jumper. As you can see, there are a lot of jumpers in this series. So I have just connected this point A to this point B with the jumper. So like this, you can put your components on the breadboard and you can make a circuit out of it. So during our practical session with the software later in this workshop, we will be first learning this breadboard, because obviously breadboard is the first stage of prototyping. So we will be first making our circuits on this breadboard. Let's move on from the breadboard. So now remember, at this stage in your project, you have finalized the components and you have finalized that this will be my schematic, this will be my circuit, this is where the sensors will connect, this is where the actuators will connect, and this is where the microcontroller will go, this is where the power will come from, and this is where the the output will happen through the LEDs or something like that. So you have finalized all of this on the breadboard. Now it's time to move on to the next stage. So the next stage is called it's called prototyping board, or in our country it's literally known as a Vera board. So a Vera board is basically also called a zero PCB. A Vera board is also known as a zero PCB. Why? Because it only has like a PCB. You have to solder stuff on a Vera board, but like if you buy the Vera board blank, there is literally nothing on it. So it's also known as a zero PCB because there is zero components on the surface of the Vera board. So this is the stage where you are making prototypes. You are not really sure that if your project is a product yet. It's like if it's survival in the outside market. So say you can make a project out of anything, right? But in order to be a product, it has to be strong and rigid, right? It cannot go out in the market and face the harsh environments and fail. So to prevent that, we do prototyping on a Vera board. A Vera board is like a simulated PCB that lets you test if the product is strong enough to go outside into the market. So if there are bugs in your circuit, if there is malfunction, say you put a wrong capacitor, which if you know what I mean, if you are from electronics background, you would already know. If you put a wrong capacitor, if you put a wrong value of a capacitor or a low capacity resistor, so that will end up in your circuit getting heated in the long run and the component might just burn off. So that this kind of stuff you can recognize on a Vera board, keep it on for, keep the product on for like 8 hours, 10 hours, do a full day testing, test out the stuff in the long run, check out the heat output, check out the other efficiency problems, check out the any voltage leakages that has been occurring in the circuit that might be there. So you, in short, you like iron out the bugs in your project in the Vera board stage. Now most projects in the college level or university level stops out here, because once you iron out the bugs, you make your final final version of your project, you submit the project, and that's it. There it ends. But if you want to go make your project into a product and sell it, make a company out of it, make a brand out of it, then you need to move on to a PCB. So let me give you a quick example of a Vera board. This is a project I have been working on. It's a small pastime project. So as you can see, it's made of cardboard. So this is a Vera board structure that I made. I bought a Vera board and I mounted some buttons on this thing so that it could attach to an Arduino microcontroller. So if I remove this, you guys will be able to see that there is a Arduino microcontroller beneath it. Okay, it just connects on the microcontroller like so. And if you press it shut like this, and it sandwiches on. It's like a shield. It's like a shield of a microcontroller. It connects on top of it and it plugs in directly. So this is made by hand, because like in Gerber boards you have to hand solder everything. So this circuit I made I wanted myself. If I now still want to change this circuit, if I want to change this path of this switch that is connecting to the microcontroller, I can do that. But when you are in a PCB, when you move to the next stage into the production, you cannot do that. Once again, that is what this Vera board is for, to iron out the bugs, to confirm all the paths, all the connections, everything before you move to a PCB. So if I now want to make a product out of this, I would make a PCB that would preferably have like more support for the microcontroller, so that it might shield the microcontroller from any damage or stuff like that. Now, since we already know there are many different types of versions of a same component, like in case of a breadboard, I already told you guys that this is a full-size breadboard. We also got a half-size breadboard, which is half the size of this, like it's half, like so. And we got a micro breadboard, which is literally just this much size. So it has like 6 rows only. It's very small. So yeah, we got those. So for Vero boards as well, there are like different versions. So in those different versions, there are mainly two significant versions that we need to worry about, which is the lined Vero board and the dotted Vero board. As you can see from these illustrations, the lined Vero board has like parallel connections, right? So you connect one like wire on the top of it, and this whole line of where you connected the wire. So say you connect the wire here. So this whole line going straight down to here. So that straight line will represent now the same like the same signal of the wire. So any signal you put anywhere in that line, it will pass through that wire because it's totally shorted. On the flip side, the dotted Vero board gives you more like more flexibility to connect any like point with any other point in whatever manner you want. So basically now, since this thing is more flexible, why does this thing exist? So these things usually exist for like ground and power connections. So you have a lot of power connections branching out to different parts of your project. You have built a big project that has many power lines and stuff like that. So are you going to sort out every one of them with your hand? That's really time consuming, right? So this line Vero boards make that transition very easy. So you connect the main power on the top of the thing, like the power ground and stuff like that, and then you connect all the other power rails to the below that. And then when it comes to signals and sensors and microcontrollers, like the intricate stuff, you go to the dotted Vero board, and then you like make the circuits as you want. So this gives you more flexibility, this gives you more efficiency. So whatever you need is, that's where you go. So the whole idea of this prototyping is to once again iron out the bugs and make an efficient circuit, more efficient schematic. So since we are done with the breadboard and Vero board, so now you're in the final stage of your like product development. So you are over the project part. You are sure that you want to make a product out of your project. You want to sell it to the market in mass production stage, and you want to make a brand or something out of it. Okay, so you know that your the pathways that you made are fine. They can run in a long run for 8 or 10 hours without getting damaged. It's not overheating. It's not anything. You have finalized all the bugs. You are at end version, like the final version of your project. Then you go to the PCB. So as I wrote below, if you guys can see, so this is the part where the beta testing of the project, which I was talking about just now, it's over. It's totally over, and you are now ready to get into the industry and sell your product. So at this stage, I'm telling again, if you are still left with a mistake or something like that, and if you go into mass production, you do not have the capability to correct it. You would have to discard that entire batch of PCB that you have manufactured, and you have to start fresh, and that will be like a huge loss. So before going into the PCB, make sure that your schematic is absolutely finalized. So yeah, we have now climbed to the ladder and we have reached the top of the chain, which is the PCB. So now let's see how a PCB is actually designed. So these are the steps for designing a PCB, and frankly speaking, this is what you are waiting for, right? So let's start with the schematic. As I was always telling, schematic is basically the map. You can call it a map. Like in a city, you have a map of where each building is, what each building does. Schematic is a map of your circuit. It shows what component is connected to what component is connected to the power, the entire thing, the geography of your circuit. So it shows where the signal is coming from, where the signal is going to, where the power is coming from, where the ground is connected to, and what your circuit is trying to achieve. So the schematic is the thing that you need to get right, as I was saying. So if you get the schematic wrong, the whole purpose of your circuit working gets defeated. So this is the most important part, schematic. It's like a graphical, and also one thing is the schematic is like a graphical representation. So you don't like use actual pictures. Yeah, you can use that. It's for like beginners and stuff. But when you are into advanced schematic making, you have a symbol for everything. Like this schematic, you see that big square thing in the middle. That's a symbol for an IC. So in here, that's a symbol for an Arduino Uno. So once again, it's a microcontroller. So it has these many pins, and it's connected to these. So this tiny stuff, that's a transistor, that's an NPN transistor. Once again, transistors will also have different symbols. An NPN transistor will have a different symbol, and a PNP transistor will have a similar looking but slightly different symbol. It will not be the same because the two of them are representing two very different products. And finally, these square things, these are LEDs. So as you might have guessed right now, that it's like a LED circuit. Okay, the same thing that we are going to build in a moment. So PCBs. Now talking about PCBs, PCBs can be as simple as an LED circuit like this, as I was telling. So this is a custom PCB made by us as well. So yeah, hold on. Let me show you this properly. Okay, so you are not unable to see parts of it because my green screen is green and this PCB is also green. Anyway, so yeah, this is a very simple PCB. As you can see, there is a couple of LEDs. There is a slot for the microcontroller right here, and there are some potentiometers to adjust the brightness of each LED. Okay, so this is a LED circuit, very simple one. And now on the complicated side, look at this. Yeah, that's a computer motherboard. It's from 1995 and it's pretty complicated. It's from like 15 years, like no, 1995, right? So 20 plus 15, it's from 35 years back. But still, it's pretty complicated. It has like multiple layers. It's like you can say it's like the highest point of the PCB design. While you can say this is like a double-sided PCB, this is almost the lowest, simplest PCB design, and this is the like the heights of complication. So it has like 5 or 6 layers, having like communication is happening between these layers as well. So yeah, this is pretty complicated. But believe it or not, this and this can be designed on the same software. That's the beauty of PCB design. If you have the skills, if you are patient enough, if you spend enough time, you can design this. Or you can spend no time at all. You can be you can be in a hurry and you can design this. It depends up to you. Okay, so that's out of the way. So now we are designing a PCB. Okay. Now let's focus. Now there are certain parameters of a PCB. As I said, PCBs can be like like this small or this big, right? So there must be different parameters, right? So the simple PCB that I showed you and the computer motherboard that I showed you cannot be the same, right? So there needs to be something different, right, about them, because one has only one single layer and the other has like 5 layers, but both of them have the same thickness. So how is that possible? So this is possible because of these parameters that you can select. First comes is the double layer PCB, single layer PCB, or multi-layer PCB. So these things depend on the complexity of your project. How many parallel lines you want going in a single place, it depends on that how many layers of PCB you will need. Next we come to the rigid PCB, flexible PCB, and rigid flexible PCB. So as I already told you, PCB is basically a sandwich of wires and like a insulating material in between, right? So a rigid PCB is basically like have a rigid insulating material, like as I already told you, fiberglass. A flexible PCB has like a flexible material, like there are some heat resistant plastics that are used, that are employed in manufacturing these flexible PCBs, and then we have rigid flexible PCBs. So these are like a combination of rigid PCBs and flexible PCBs. Like for example, let's say the old flip phones. Remember those, right? It flipped open and it flipped close. So it has a screen on the upper part and it has like a keypad on your lower part. For example, right now my laptop, your laptop, anybody's laptop. So the laptop basically has the screen on the upper part and the all the processing and the keyboard on the lower part. Have you guys ever thought that how the signal gets transferred from the bottom layer to the top layer? It's basically a flexible rigid PCB. So the top layer that has a screen, the webcam, and the Wi-Fi antennas, that is like a solid PCB. The bottom layer, obviously, your motherboard is a solid PCB, and then connecting those two are wires or flexible pieces of PCBs. So basically, these two solid pieces are connected by a flexible PCB. That's a very real example of a rigid flexible PCB. And then there are high frequency PCBs. So basically, when you put a PCB in a high frequency or like a, high pressure region, it's its properties alter, because certain like components that are normally used to make a PCB to keep the cost efficient does not behave well with high frequency or high pressure regions. So for that purpose, you have special materials to build the PCB for this kind of applications. So high frequency PCBs tend to be more costlier than normal PCB, but the quality also outshines the normal PCB. So as I already told you guys, you choose the process, you choose the material depending on the situation you have. So, and finally we have like this aluminum-backed PCBs. So these things are like for, as I already told you, high pressure regions. So that was a high frequency one right there, and this is like a high pressure region. So it has extra support of an of aluminum blocks, like with a bit sandwich between that insulating material I was telling about. So what that gives is like it gives more strength. So normal PCB, if I like bend it hard enough, it will break. If you bend your phone hard enough, it will break. But these reinforced PCBs, you like beat them with a hammer and they will not break. Maybe the components on the top and bottom will get damaged, but the PCB itself will not break. That's why aluminum backed PCBs are, that's why these are for. These things are for high pressure requirements. So now that we have learned different types of PCBs, now let's get like deeper into the structure of a PCB. What is inside a PCB? Now, these are the PCB terminologies. Okay. Now, in a moment, I will show you the detailed structure of a PCB, like a sandwich. You have the bread on the outside. You have like a layer of veggies between, and then you have a layer of meat in the between. Similarly, a PCB is basically also a sandwich, but it consists of some other stuff that I am going to show you right now. But before that, to understand what that layer is, we need to understand some terminologies like these. So first is the copper foil. Oh, wrong direction. First is the copper foil. It's basically it's like the material that makes up the soldering pads of a PCB. So if you have seen a PCB, there are certain points where you can solder. You cannot solder anywhere you want. There are certain exposed points of copper that you can solder. This is where the copper foil comes into play. So the copper foil is deposited on the top of a PCB so that you can solder there your components. And these are by design, as you will see, as you guys will see in a moment. Next is copper plating. Copper plating is actually the plating of the copper on the whole PCB. That is before you start working on like the PCB design. So you get solid copper plates that have like like a fiberglass material in between and copper plating on both sides, and then you carve out the PCB with that plate. Next is solder flow. So solder flow is basically okay. So yeah, maybe solder flow. There's some glitch on there. Anyway, solder flow is basically the points at the holes which allows the solder to flow from one side of the PCB to the other side. This is usually because when we want to connect both layers of the PCB, say I have one component on the top of the PCB, I have one component on the bottom of the PCB, and I want to connect both of them. Let me show you an example. So right here, I have the bulbs on the top of the PCB, and I have these resistors and other stuff, all other stuff on the bottom of the PCB. So how do I connect this? With these solder flows. See these dots? These are solder flows. So these basically connect the top of the PCB to the bottom of the PCB. So these things pass through the PCB and connect both the layers on both the sides. Next comes the solder mask. The solder mask. So the solder mask is basically like a layer on the top of the PCB that prevents, as I already said, you guys cannot just solder a PCB anywhere you want, right? You need to get these fixed copper pads and solder there only. So the solder mask is basically everywhere except the copper pads. So basically there is a mask of a insulating material so that you cannot solder there. That's it. Trace is basically those copper lines running those are traces. Basically, they are replacement of wires. They are conductors that actually carry the signals from one place to another. So the lines you are drawing, the schematic, the connections you are joining, those are the traces. And finally, silk screen. So silk screen is basically a layer where the actual instructions are written. So say there is a place where you have to connect a bulb, like LED. So those are two-leg components. And then there is a place where you have to connect the resistors. Resistors are also two-leg components. So how you are gonna understand that where you connect the LED and where you connect the resistor? So that is done by the silk screen. The purpose of the silk screen is to have certain specific instructions on the top of a PCB. Those are literally like minimalistic, like they only have the names of the component in a short form or stuff like that, so that you can understand from that reference that where you have to place which component. So moving on, let's learn the structure of a PCB. So since I have been talking about PCB so long, you guys already know the structure of a PCB. So it's basically copper layers with like a layer of insulating material sandwiched in between. And then we have these copper lines going between that layer, which are known as traces, and which connect the components to ensure a good signal flow and thereby complete our schematic. So that's basically the structure of a PCB. Next, this is the picture I was talking about. So there, as you guys can see, so this is basically the substrate. So substrate is basically nothing but the the insulating material I was talking about. So that once again, this is a PCB terminology. It's called a substrate. Anyway, so after that is a copper layer. So this is the layer that actually conducts. This is the layer where we actually the traces, the lines. Then we have the solder mask. So the solder mask, as you guys already know, it's a layer that prevents you from soldering anywhere on the PCB except the places where there is the pad cut out for tapping into this copper layer. And then on the top of it, there is a silk screen that contains the instruction that yeah, you put the LED there, you put the resistor there, so that you don't mess up, basically. Now constructions. So this will give you a little more insight into that supporting layer I was talking about. So as already I told you guys, this is here mostly fiberglass as written here, and then there is the most commonly used base material is FR4. So FR4 sounds like a compound or like a alloy, right? It's not. It simply means fire retardant 4. So like a few years into the PCB development, after it got released to public in 1948, they realized that PCBs can catch fire actually. That's really pretty bad because they used ink in the PCBs, right? And the fumes coming out of the ink is also hazardous. So on one hand, you are having like a electricity hazard. On the other hand, from the burning fumes, you are having a toxicity hazard. So to prevent that stuff, they created a compound to use as a silk screen on the top layer, so they created this compound called a fire retardant. So number one, it didn't give out toxic fumes, it did not and it did not like catch fire easily. It's basically like a paint, a sort of fireproof paint, you can say. So and that there are like many versions of it, like iterations of it, and FR4 is simply fire retardant 4. So it's a fourth version of the fire retardant paint. So like like more versions up you go, it's better and stuff like that. So if you use FR16, that's far better than FR4. And then there is Captain. Captain is basically you can say heat resistant plastic. So it does not react to heat as normal plastics do. So for example, if you put a lighter or a soldering iron and touch it to a plastic stuff, it will melt, right? So Captain has like a very high melting point. So it's not impenetrable. Nothing is impenetrable. So while these normal plastics melt at below 100 degrees, that Captain stuff melts over like 600 or 700 degrees. So before that thing melts, everything else, every other component on the PCB will have melt, and the PCB will be essentially useless before the Captain layer actually melts. So yeah, that's useful. And then as I was talking, so these are single layer PCBs. So as you guys can see, there is only one substrate or the fiberglass layer, one copper and one solder mask. So it's on one side only. Okay. So say this is the substrate, the PCB is on the top only. Okay. Then comes the double layer PCB, as the name suggests. Double layer PCBs have both same thing. Again the insulation layer is in between, and then we have a copper layer and silk screen on top. Flip side, we have a copper layer and silk screen on the bottom. Okay, same thing, sandwich. And then on multiple layer on multiple layer PCBs, and we have like layers after layers after layers of the same stuff. And then we have these small tubes. Okay, these copper tubes that are like used to carry signal from one layer of the PCB to the other layer. So as you guys can see, this drop down tubes. So see, this tube is dropping down all the way from one side to the other side, connecting all the layers. And then this tube is dropping down a little, like this one. This is dropping down a little, and then these tubes are not even visible from the outside. These are just connections between the internal layers. So that is the level of technology that has been used in this one. So yeah, computer motherboards. So these things use like inter-layer connections. So we even don't know whatever connections is between this layer and this layer. So there are like 5 or 6 layers just in this thickness only. So yeah, it's pretty complicated. Now, components. So since we're talking about layers, there are 2 types of components that you select, that you have to select with as well. So one of them is called a surface mount component, or SMD, and one of them is called a through-hole reflow, or THR components. So these are the following differences. Oops. As you can see, the SMD component, or the surface mount device, mounts on the surface on a copper pad, right? And the through-hole reflow, or a THR components, needs a total like like a total hole to pass through. So it can be soldered on this side, it can be soldered on the other side. So this is basically this straight line is basically the PCB. This cross section is the PCB, and this is a through-hole example component, and then this is the SMD example component. So once again, if I show you in practical life, in this PCB, all of the components are through hole, first of all. So if you guys can see, there is the bulb right there, and then there is the soldering, right? Once again, there is the bulb right there, and there is the soldering on the back of it. So basically, through hole components are getting soldered on the other side. So you place the component on this side, you solder on the other side. You place the component on this side, you solder on the other side. The through-hole component means soldering on the opposite side. But surface mount device, on the other hand, does not need that. So surface mount device, you can just slap on the copper pad and you can put some solder paste in between. It can hit it and it will like get soldered. So since you are getting a little less area on this surface mount device than a through-hole device, like soldering a surface mount device is a little tricky than a through-hole device. But these things have their own advantages. For example, if you want to go through multiple layers, so say you want to connect it to all the layers, say it's a ground wire, you want to ground all the layers, then you can use a through-hole reflow. So it will connect the pin to straight to all the layers through the PCB. Doesn't matter how many layers the PCB have. But if you want to use only tap one layer, so then you can use SMD component, because see, if there is a layer over here or here, they are not concerned with whatever is up there. This one is only connected to the top layer only. So these are the examples. So as you guys, I already showed you, these are the through-hole components. See, it goes through all the layers of the PCB and solders on the other side, right there. Okay, I'm getting some questions. What is a multi-layer PCB? Okay, right. So these are the questions you guys have to answer. So basically, if you see in the bottom part of the screen, there are some questions. You guys answer these questions, you guys get a scholarship. All the best. Anyway, so back to the studies. So this is the component side and this is the solder side. So as I told you guys, for the through-hole component, you place the component on one side and then solder it on the opposite side. Okay. Next is the surface mount component. As I already told you guys, it works on this solder pad technology. So basically, there are small copper pads on the PCB, and then you place a component on there, and then you place some liquid solder, and then heat it to like melt it and like place it there permanently. So as you guys can see, these are the contact points where you place the solder, and then you just do it. So since these are like so small contact points, soldering iron cannot be usually used because the tip of the soldering iron, no matter how like thin, would like have a little bit of vibration, because you know our hand has a natural frequency. You cannot keep it absolutely still. It's very hard. So a easier way of doing this is basically called a solder reflow. So in that case, a soldering like the circuit that you are doing is either placed on a very hot surface to induce heat on the whole circuit so that the pad gets heat automatically, or you can use a hot air gun. So basically, as the name suggests, hot air comes out of it. You can adjust the temperature, and then you can blow that hot air over this soldering pad. It will get heated up, and then this thing will melt and then seal the like the bond. And as you can see from this, it emerged in 1960s. So as I already told you guys, PCB was invented in 46. It was made public in 48. So from 48 to 60, they used only these surface mount components. They used only these they used only these two-hole components, and then they realized that no, that logic I was telling you guys, that we need to tap one of the layers, but for a two-hole component we have to tap all the layers. That's the necessity. That will make the PCB bigger. So they said no, we need to make a PCB smaller, and then we have to tap the individual layers. And then in 1968, sorry, in 1960, they developed this product, surface mount components and surface mount technology. And then the designing of the PCB. So finally, we are over this theory part for the moment. Actually, there are other parts as well. And now we can jump into the software, and you can we can just build a PCB for ourselves. We can build a, as I said, from the step to step. First, we will build a breadboard, then we will build a schematic, and then we will build a PCB finally. So yeah, let's jump to the software. Before that, Arjita, would you like to add something?
No, continue, go ahead.
Okay. Okay, so once again, we have a lot of options in developing a PCB, right? So the industry standard is basically either Altium Designer, which is a very good software, and then there is Eagle. So these two are mostly used by the professionals. Right now, we will be using Fritzing instead. Why Fritzing? Now you guys might ask me that why Fritzing? There are other softwares. There is Proteus. There is KiCad. So there are like a lot of options. Why Fritzing? So Fritzing is basically the only the only one I know that lets us like have a visual representation of the component that we are picking and dropping on the breadboard view. Okay, so I think that might help you guys since you guys are beginners and stuff like that. So let's do that. So I have loaded up Fritzing. So let me put it on screen. So okay, so this is the UI of the Fritzing. So this is a welcome screen and stuff like that. To make a new circuit, just go to Files and click on New. Also, you can do New Sketch, but that would mean that you first have to make a sketch. But we want to start from a breadboard perspective. So let's go to File and click on New. Give it some time. Okay, so as you guys can see, we are treated with a. I closed it accidentally. Anyway, never mind. Let's do it once again. No harm, no foul. So it's loading the sketch actually. Yeah, there it is. So let me just minimize it and close this other window. And there it is. So as you guys can see, we are greeted with a breadboard like this full size breadboard as I was already showing you guys. And then there are a lot of components. Like they have like a big library by default, and you can also like buy some add-on libraries. And there is also a component designer if you want to design your own custom components that might not be here, right? So it's a big advantage. And on the other stuff is like that. It's not a crack. It's not a or it's not a paid. It's neither of those. It's like a free software. So you don't have to do like go through any hassle. You won't have to pay for it. You don't have to crack it or hack it or stuff like that. So basically, it's free. So you guys can start with this thing. Okay, this is a best. This is like a very good option for the beginners. And I'm not like suggesting that you stick to it. You start with this. You get to like advanced level, and when you think that yeah, I'm ready for the advanced level, I can handle more now. I don't need this graphical stuff. I can directly jump into the schematic. Those symbols are programmed into my head. When you guys feel confident that you guys are at that level, just switch to other stuff like Proteus or Altium or Eagle. As far as I know, Eagle also has a free version, and that also has plenty of features. So you guys can move to Eagle. So yeah, like for the moment, let's start and design something. So as I told you guys, like we can simply design a LED pattern circuit, right? So let's do that. So for the LED pattern circuit, the first thing we are going to need are LEDs, right? So let me get some LEDs from here. Move it to the side. There's one LED. I'm going to just place it here. There's another LED. So if you guys can see, when I place the LED right here, these things go green, which means that these things are connected in. Let me just move. Okay, so when I press these LEDs, these whole lines go green. I don't know if you guys can see or not. Let me zoom in further. Yeah, so these lines go green, which means that these things are vertically connected, as I was telling you guys about earlier. So yeah, let's put another one. Let's put yours. Another one. Okay, now we have made a consistent pattern. So I have 5 LEDs here, and now we can connect them to the Arduino, and then we can start developing the other stuff. So first, we all know that the ground connection of the LEDs is a common one. So let's first do that. So this is the ground, if I'm not wrong. So if you just point on the limb, it will show you. Yeah, it's a cathode pin. So now I will connect this ground. So you have to hold it and drag it to connect. Like so. Not connect from the one was intended. So it's really easier with the mouse. I'm doing with a trackpad. So it's a little bit difficult to hold on to the controls. Right there. Okay. Yeah. That's done. Then let's short out this like so. And short out this. Then short out this. Okay, all set. We have connected all of these negative lines. Then we can connect a negative line from there to the Arduino. Next, this LEDs need a current limiting resistors, because let me give a TLDR to the people who are not from electronics. An Arduino supplies 500 milliamps, and this LEDs only need around 30 milliamps. So it's like a lot more current, which in short is bad. The LEDs will just go boom. So to prevent that, let me put a current limiting resistors. Like this, you can also spin your component. I'm going to select a resistor. I'm going to press and rotate. So yeah, let me place it right there. Rotate this one as well. Bring it right there. Right there. 3 down, 2 to go. Now, whatever designer you guys might be using, the interface will be the same. Like you guys will have same kind of components and stuff like that. You might not have this breadboard view, but the schematic and the PCB view that I'm gonna show in a few moments will have the same stuff. So, yeah. So this is basically the structure. Now the ground is already set up and the resistors are set up as well. So let's now go ahead and add a brain to this circuit, which is an Arduino. Okay. So the simplest way of doing that is just going to this categories. So if you guys can see, there is written code over there, which means these are the code components. Go a bit down, you will find Arduino. So it takes a little bit time to load actually, but it will have, see, this many microcontrollers. And the first one that we will have is a Uno. So just take a bit of time into consideration that whatever microcontroller you're going to be using, you want to use the same one here as well. On one hand, this is cross-compatible. On the other hand, if we just jump to the PCB view, we are not there yet, but just for reference, let me show you something. Since we have loaded a microcontroller, see, this stuff gets automatically loaded. So this is basically a blueprint of the Arduino. So now when we make a PCB out of it, it will automatically turn into a shield that you can directly place on the Arduino. You don't have to work out any wires or stuff like that. So it's like very good for if you're making a simple design, or if you guys are beginners. So that's why I would recommend to select a model that like corresponds to your Arduino that you're going to be using in actual life. Then you can just drag and drop and place it on Arduino. So we are going to be using an Uno because that's very beginner friendly. So I have selected an Uno, and this thing has concurrently loaded a Uno blank right here. So let's go to the breadboard view and connect the stuff. Wow, you guys are interested. You guys are interacting with the questions. That's fantastic. Let me now zoom in here. Okay. Now let me put the cursor over here because we want to zoom in right here. Right here, like so. Okay. So time to do the connections. Need to get used to this thing. Okay. So let's make the connections. The first LED I will place it in pin number 2. So drag a wire from here to there. Okay, done. Fantastic. Next, I will be doing the next LED to pin number 3. Okay. Pin number 3. Here we go. Okay, fantastic. Next up, pin number 4. There we go. Next is pin number 5. And then pin number 6. So as you guys can see, the wiring is not optimized at all in here, but it's not required, you know. This is why the breadboard is important, because you guys don't need to optimize the wiring. You guys don't need to think about optimizing anything. Okay, this is just the phase where you select the components and then just whatever that only. Optimizing about the wiring and stuff like that, that comes in later. So now we have connected the Arduino to the resistors, to the LEDs, and now we are ready to go out to the schematic and make the PCB. Okay, am I missing anything? Okay guys, let's take a little break and let me ask you guys, what connection do you guys think is left in this structure? So I'm gonna zoom in, I'm gonna let you guys see, and one of you guys tell me what is still missing, because there is something missing with this. Okay, now, fantastic, ground connection, yeah. So basically I didn't connect the ground. So the ground will go from here to right about here. So now we are actually finished with the connections. So there is our circuit, there is a whole circuit. Now let's go down to the schematic. So now things are gonna get serious. Let me just move out of the way. So there is a whole circuit. So we have made the ground connections and we have made the LED connections. So now let me go to the schematic. As you guys can see, it's a huge mess. And it is supposed to be, because this is like just a bunch of parts. And these lines, they denote where these things are supposed to go. Okay. Now what you guys can do is just spin this thing until they get into shape. So, since the connections on that side, so I will do this. See, the connections are already getting sorted. So I will just put this into focus mode. This. Let me just out of the way. So this is the microcontroller that is sorted. Now let's take each of the LEDs out one by one. Okay? So it's a huge mess. We will need to be very patient with this. So this is the first LED. Yeah, there it is. And then we select this, take this out. Okay. Now we spin this resistance into place, like this. Okay, it's in place. Fantastic. Again, do the same with this. 1, 2. It's in shape as well. Fantastic. Now let's see what this is connected with. So this is connected with this. As you start sorting them, you guys will notice that this connection is transforming. See the ground wire transforming right there. That is because auto routing is working in the background as well. So it means that the computer is helping you. The computer, it's not as intelligent as you, so it doesn't knows your ideas, but it's trying to help you to sort this thing out. Okay. So these are LED 4 and 5. Green one is next on the list. So let's bring it here. This level was probably this one's that came off. Yeah. This one should be probably right here. And this one should be probably right here. Rotate it. So by double clicking on this thing, you guys can also change the name of this component. If you guys like, because this is after all, this is what you will be getting printed on the screen. So if you want to like name your component something different, something that might be easier for you to understand, you guys can do that as well. So let me this component, place it in position. We have already connected to this position. Spin it. Oh my god, I did auto routing. Auto routing was not needed at this point. So let me cancel it. Cancel it. Instead of flipping it, I pressed auto routing. So auto routing will be useful in a bit, but not at the moment. Right now, we just want to rotate like this. So that the LED is getting position. So we don't want to place the wire just yet because it's not ready to receive the wires yet. So the next should be orange one. And now let's spin it. Put it in position. Let's take the LED. That's the LED 1. This goes to further right. Now I'm going to place this LED and I'm going to spin it. As see, the ground is routing itself. So I'm going to accidentally place auto routing. My bad. This. So this LED is placed as well. If we place a resistance in position, also. And finally we are left with only this one. So let me flip it, let's rotate it. So bring it in position like this. So now you guys can see that this is totally done. It's totally has taken shape. So now we can press on auto route. So you can do the wires by yourselves, and you can press auto route. So since you have already placed the components in their position, auto routing will be as efficient as doing it yourself. Excellent. See how simple that was? Automatically connected everything. So this wire is going right there. This wire is going right there. So see, no confusion. So now let's go to routing and press on show unrouted. So then it gives me that there are no unrouted connection. Okay, so which means that I have successfully routed all the connections. So it's like a check to see that if you are doing the things correctly or not. If there is any wire like unrouted, it will show up and you can like recognize that yeah, this wire is not routed. So now let's get to the missing part. Now see, a little bit before this thing was not configured at all, but now look at it. Everything is configured in here. Everything is connected by these transparent lines. These are transparent because we have not routed them yet. So the technique that I showed you guys a little bit earlier in that schematic, same stuff. So basically, we put the resistors, we put the LEDs, and then we finally auto route. So this is the first one. We're gonna rotate it until it gets into the perfect orientation. Then we are gonna. It's not the one supposed to be. We keep the LED right there. Okay. So as you guys can see, as soon as I moved it to the closer to this ground, it automatically connected to this ground. So yeah, this optimization will happen on itself. You just have to keep your eyes open for that. Put here, select it, rotate it. Place it in position. Find the LED connected to it. Pull it into position as well. Like so. The LEDs are not good optimized. Let's do that as well. Oops. Accidentally drew a wire there. Select the wire, right click, and delete wire. Because we don't want the wires just yet. Yeah, so next up is this one. I'm guessing this one. Yeah. Accidentally drew the wire there too. Delete wire. This is the next. So let me just. It's already on maximum brightness. Rotate it. It might look a little boring, but that's the process. You know, as I say, this is the way. So 3 done, 2 to go. Oh boy. So these mistakes will happen less if you use a mouse. I suggest using a mouse so that these things don't happen. And it will happen again. Okay, let me just quickly do this. with the proper stuff, and then we'll be back. So so this is the sixth one, and that's the fifth one. Just move this wire out of the way. We can delete it later. Ah, now we have moved it. So now let's delete wire and delete wire. Let's give it a spin. 1, 2, 3. And place it in position. So the name tag of this thing. Let's place it somewhere there. Then get the LED in position. And then spin the LED like this. And finally, let's place R5 in here. Place the LED right about there. And then, as usual, spin it. So if you guys look at the PCB now, since we are doing it only 5 LEDs, we have a lot of space. So let's spread this out a bit. It will look better, in my opinion. Yeah. Now that it's totally done, hold on. Let me just make myself visible. Now that it's totally done, we can focus on the routing. Okay. So let's do that. We can just draw it by hand, like this. Okay. We can do that. Or we can take a more optimized way by just pressing auto route. Let's just done. That's all it took. One press, finish it up. And as you guys can see, like once again, auto route can fix everything. So this thing is almost overlapping pin number 7 right here. So to fix that, let's do some. Yeah, like so. Now remember, one rule of PCB designing is never do a 90-degree. So whatever you guys do, never do a 90-degree turn. Just keep it below 90. I mean, obviously you guys can guess with your eyes that it's less than 90. So just use the imagination of the eye and keep it below 90. Further, we can go because this. Now we can coordinate this thing. Right there. As you guys can see now, everything is far apart. Nothing is in the short territory. There is no shorting anywhere. But just to check this thing out, just go to routing and design rules check DRC. So just do it. It will check your design and it will give you the result. So it shows your sketch is ready for production. There are no connection or traces, overlap or too close, which means that there is no chances of shorting out or stuff like that. So after this is done, let me just remove. As you guys can see, our PCB is now done. So if you guys want to see it from the other side, just press on this one, bottom layer. That is the bottom layer, and this is the top layer. So if you guys can see, this is on the other side, so the traces are like less visible because it's on the other side, and on this side the traces are more visible. So yeah, this is totally optimized. So you guys can say that you guys have now successfully created your own PCB. So yeah, now all that is left is to export it. So let's go to export PCB, and now if we press on this small arrow right here, we got some options. So we can make etchable PDFs, we can use etchable SVGs, and we can use Gerber files. So let me tell you what each of these things does. So etchable PDF is basically a format that you can use to build a PCB at home. Okay. So that will be our next topic. I will just shortly show you that how you can build a PCB at home. So that's etchable PDF. Next is etchable SVG. So basically PDF and SVG. PDF is basically a printable file and SVG is basically a graphic file. So say you are etching it using something like a CNC machine or something like that. So then you will export an SVG. And then say that you are sending it to professionally produced. Okay. Professionally produced and manufactured at some certain distributor or PCB maker like JNC PCB in China. I don't know right now it's working, it's delivering in India or not. And then there are many Indian PCB designers as well. If you search for it, you might find 3 or 4 in Kolkata as well. So you can, if you are sending this off to those people for printing, then you can do Gerber files. So Gerber files are basically like render of each different layers. So it will print one layer for the copper only. It will then print another layer for the silk screen. It will then print another layer for the solder holes or traces and stuff like that. So it makes the thing a lot easier. In PDF also you will get the Gerbers, but in like image format. So I'm saving it in the desktop. So let's see. So let me get to my desktop and then. Okay. So it's exporting. It's on my other screen right now. It's exporting. Okay. Exporting a lot of files. So let me show you what this exported. Okay. Just a second. So this is my other display, quite exported. So as you guys can see, these are the files that it exported. So let me show you how this is done. So this is, as you guys can see, there is nothing on it. So this is basically the blank layer. Okay. So this thing goes layer by layer, as I just told you guys. So this is a blank layer. Okay. Next, let me show you this. This is basically the boundary layer. Okay. This is the bottom layer. So as you guys can see, this is the Arduino. These are the LEDs, the resistors, and these are the LEDs. And then this is the Arduino. So this is basically the layer where the bottom layer or the soldering will be done. These are the solder pads or the holes. Then this is the bottom cell screen. Since we don't have any components on the bottom, it does not have anything written on it. This is the top layer. Once again, same holes. This is white as well. Okay, then there is, this is the total silk screen of the top. Okay, so as you guys can see, this thing contains all the numbers. This is the Arduino's LED 54321, and then this is the R5, R4, R3, R2, R1. So this is the registers, and then this is the Arduino's default uh, legend or default mapping. So yeah, that's the thing. Okay, here. So yeah, so basically you can say that our PCB is basically ready for production or anything like that. So next we will discuss about how we can like build a PCB at home, okay, without any like setup. We will need some kinds of chemicals or stuff like that. I will talk about in a moment. But we won't need like professional big machines and stuff like that. It's very easy actually. So before I go into that, Arjita, again, would you like to add anything, or would you like to ask any questions?
Nope, go ahead.
Okay. So basically, let's go back to the presentation. So PCB design done. I hope everybody understood. Now, this is not the end of the line. Like there are a lot more stuff for PCB designing. Okay, you guys have to learn a lot more for this. Just this is just scratching the surface, as the as the tagline said, introduction to PCB design. So there are a lot more advanced stuff. We also have like a 3-day workshop on PCB design that is much more detailed, and it's coming up in a like a very short while. So you guys can register that as well. So you just can register for that as well. It's a lot more detailed because obviously I have only 3 hours and it's not enough for all the details. So just a minute. Okay, let's continue. Now we will go into the fabricating the PCB. So this is a highly experimental part, as I already told you. We will be using some very toxic chemicals that like it's like life-taking toxic. So it's very toxic. So that's why I put a disclaimer in the PPT as well, so that you guys get a little bit warned that we're about to enter a very dangerous territory. So we're going to be using chemicals like ferrous chloride and stuff like that. So it's very dangerous. And even after you use the chemicals, you cannot just throw it away. Okay? It needs to be processed and then thrown away. And also you cannot buy this kind of chemicals in the shop next door. You need to go to specific chemical shops to buy these chemicals, and you need to have like a professor's license or chemist license or something like that. That you are a professional that is experienced in experimenting with this. So if you want to know my advice would be do it under supervision of someone that is already qualified to do this kind of stuff. A chemistry teacher or lab assistant or someone like that who is used to handling these chemicals. And I would say that you know mm, like take him to the shop as well. So if you want to buy these chemicals, so that will be easy for you to procure this. Otherwise, you could get in a lot of trouble for getting these chemicals, because these things are like really toxic chemicals. You know, so as I already mentioned right here, is that just get a supervision, get someone who knows what they are doing with the chemicals, and then you're good to go. So since we are fabricating PCBs, once again, it's very dangerous. So disclaimer. And then yeah, let's do this. So then we have 3 steps of making a PCB. Okay, so first is track making. Okay, next is legend printing, and then is basically masking. Okay, green masking. So it's written here green masking in the bottom, but it's only because it's green in color. The mask can be like yellow, it can be black. If you are ordering professional, it can be red, like any color you want to do. Okay, when I get to the masking, I will tell you guys how to change the color and stuff like that. So first of all, it's track making. Track making is basically, as you can see from the picture, is basically making the traces or the copper traces or the connections of the PCB. Okay. Okay. One more thing is, for simplicity, we are here. We'll be building a single layer PCB. Okay. It will have only one copper, one silk screen, and one soldering holes. Okay, on one side only. So multi-layer PCB, it's a little bit complicated, and you cannot really make it at home. It involves like sticking 2 PCB layers together and stuff like that. It's very complicated. It works on like a micron level. So you cannot do stuff on micron level with hand, right? You need laser cutters and stuff like that, advanced stuff. So we're gonna be making simple singular PCBs here. So track making is basically getting those traces, those copper connections and stuff like that. Legend printing is basically, as you can see from the picture, is silk screening. So basically, you print those stuff like what writing goes where, like what are the name of the components and stuff like that. And then masking is basically, like putting the layer, insulating layer on the top of the PCB so that you cannot like access the solder everywhere and anywhere, because otherwise it will defeat the whole purpose of the PCB. If you get these two thin wires get short, the whole purpose of the PCB gets defeated. So that is why masking is important. Now let's get at the shopping list or the things you're gonna need. Yeah, the thing that you're gonna need is the exposed skin. Okay, so screen is basically what is used in screen printing. So people who are like acquainted with how T-shirts are made and stuff like that, we already know from this. The same way T-shirt prints like this are getting printed. So screen printing, same thing we are gonna use for the PCB, just different kind of ink. That's it. If you don't have access to a screen printing, it's pretty easy to replicate that as well. So screen printing is useful because you can use the same screen again and again with just this swiping motion. But if you don't have a screen and you need to do like a one-time experiment, so don't need to make this expensive screen. All you can do is buy some transfer paper. Okay, you will get in any stationery store. Just go there and say I need some transfer paper. Okay, it looks like normal paper, but it's a bit different because the ink on that dissolves when heated. So take a transfer paper, buy some transfer sheets, paper sheets. Go to like a shop that has a laser printer. Okay? Inkjet printers won't work. Laser printer, and get the design printed from a PDF, and then like press the design on the copper board and just heat it with the like iron. Like do like a steam setting, which is like the highest rate, and press the iron, like not soldering iron, like like cloth iron, like what you use to press your clothes. Yeah, that iron. Just press it against that paper, put it on the copper, and press it against the paper, and the design will be transferred on the copper layer. Okay. And now, what copper layer I'm talking about, we will see in a moment. Next is circuit blue. So this is basically the different ink I was talking about. This is what we will use to make those copper connections. Okay. So this is a very specific high-end PCB making paint, and that's why it's maybe a little bit expensive. You guys might find some cheaper solutions, so you can go with it. It's not necessary to use this compound only, but make sure that it's PCB class. It's not normal paint. Otherwise, you guys will make a big mess, and the PCB won't work obviously. Next, you will need is solder resist cream. So this is basically the stuff that we will be using to coat the whole thing. So the resist is basically the screening layer, so the top layer that will prevent it from rusting, from accidents and stuff like that. Then is reducer. Reducer is something but basically paint thinner. I think you guys already know that stuff. Like it's used to thin the paint, because these two are like PCB specific items, but in reality these things are paint only. So you need a thinner with that. So that's what reducer is. Then the most toxic stuff, ferrichloride. So this thing is like a very concentrated acid. Okay, and if you dilute it, it won't work on the PCB. So you need it to be concentrated, but it is very dangerous when it is concentrated. And as I said, it's acid, so it will eat on anything except maybe plastics and polycarbonates and fiberglass, like plastics compound, plastic chain, polycarbonate chain. Except that it will eat on anything. It gets on your hand, it will burn. It gets on leather, it will burn. It's very toxic, and if you obviously if you since it's so toxic, if you breathe the fumes coming out of it, it will burn your throat. So stay in a well ventilated area, and if possible wear some mask or something like that. And then there is this catalyst. So basically, as I told you guys that you need highly concentrated ferric chloride. Now the concentration that you need is an industrial standard concentration that you won't get in a normal chemist shop. So what you can do is you can instead buy a chemist shop level concentrated ferric chloride, and then use a catalyst with this ferric chloride for the reaction to go in the same way. And next is finally this copper clad board. This is what I was talking about earlier when I said about the printing and stuff like that. So these are the boards. This basically is a like a plate of fiberglass. It's coated with copper plating, like a thin copper plating, so thin that you can scratch with a screwdriver. So don't scratch it. So yeah, that is the copper clad board. And finally, this PG. So this is basically used for that screen printing. So it's the stuff that you pull. You put the screen on the copper board. Now since we are doing the screen printing, let's focus a bit on the screen. So this is the circuit. So these are the traces that will be printed on the copper. Next is the green masking. So this is the top masking. Okay, that will prevent this circuit from getting accessed on the unwanted places, and it will only allow these small designated solder spots for the circuit to access. And finally, there is this legend. So legend is basically the silk screen that will have all the writings and stuff like that. So let's get on with track making. This is the most important part. So pay attention. So first thing, we are buying this copper board from a shop. The copper boards are coming to the shop from a factory, and the factory also is keeping them in stock until the need acquires that they need to sell them. So basically, the point I'm trying to make is that it's a long amount of time, and it's been in some very dirty places. So if you immediately start the reaction with this thing, the surface will be uneven. The reaction won't go as smoothly. So my advice is just wash it with like a soap water. Nothing fancy. Just wash it with soap water, and then dry it with a blow dryer. So this is a very important step, because if you dry it under the sun, it will rust, because there is air and there is moisture. If you dry the blow dryer, it will dry incredibly fast, and so moisture will not get the time to work and stuff like that. So the copper will not turn green. So if you dry it normally under the sun, you will see that the copper will turn greenish, which means it's rusting. So if you do this with a blow dryer, it will reduce the moisture content, and it will dry it so fast that it cannot rust. So immediately after drying, pour the paint on the in a container that you will be using for the screen printing, and then also put the thinner in 1:1 ratio. Okay, so half of the paint and half of the thinner. So say you need 1 ml, so 0.5 ml of paint and 0.5 ml of thinner. 1:1 ratio. That's the idea. Next is sealing of this part. So as I showed you guys earlier, we have 3 different stages on the single screen, right? But we are not doing this 3 stages in a single frame, right? So first we are doing this one, then we are going to do this one, then we are going to do this one on the same copper plate. Now if we just drop that paint on the surface, it will just spread everywhere and destroy the whole screen. So to save the other parts, we are going to apply some paper tape, okay, paper masking tape on the other parts of the side. We are going to be using this one, so we are applying tape on this one and this one, so that the paint does not flow over there. Now keep in mind that use paper tapes only. Why? Because a paper masking tape only, because they have a low adhesion, so that they do not rip off the screen, because the screen in itself is a very thin sheet of fabric. So if you pull it too hard, it will just rip off, and then the entire thing is gone into waste. You have to again develop a new screen. So to avoid that, just use paper tape. It's strong enough to prevent the paint from going there, and but it's loose enough to come off easily. So that's the stuff. Now, as you can see, with a swipe of a hand, this thing is ready. So the blue paint is on everywhere that you want the circuits to be. The traces has been marked. So now let's begin to the next step, that is etching. So now, since we have marked the places where we want the copper to be on, we have to get the copper off of the other places, right? So as you can see that the copper is on the whole PC, the whole plate, right? Because it's a total copper plate, and we want the copper to be in these blue areas. So which means that the other places like this place which have the copper but no paint, so this needs to go, right? So all the other places needs to go. So for that purpose, we will use ferric chloride and water solution. We're gonna mix once again 1:1 solution of ferric chloride and water, and then we are gonna add also that catalyst. We're gonna make a mixture of these things. We're gonna place it in a tray, and this step, this guy is obviously doing it with bare hands. Please wear a glove. It's very toxic. Please wear a glove. So this is the solution. So as you can see, as you start washing, the copper part will wash off. Actually, what is basically happening is we are introducing copper to the acid. So basically the copper is getting dissolved by the acid. And since the paint is on the copper over this part, so it's preventing the copper from getting dissolved. It's like, like you first rub the whole page with the pencil, then you put your hand and then use a eraser to erase of the other places. Then if you remove your hand, only the part where you put your hand, the pencil marking will be there, right? So same principle. We first put the paint in there, then to cover up the copper, and then we put a solution that eats away the copper. So the places where the paints are not there, it will eat away the copper, and then only this this fiberglass substrate will be visible. So this is the PCB after washing with ferric chloride. So obviously after washing with acidic substance like this, obviously wash it again and again with water 2 or 3 times minimum, and wear a glove once again. See, I put it there as well. Glove is recommended. Then this is the stage where we are washing it with water, and then we are going to rub it with a steel wool. And why we are going to do that? Because since we have achieved the purpose of keeping these coppers in the places where we want. Now we want the copper to be revealed, right? Otherwise we cannot work with it. So we are going to rub it with like a steel wool or a file or a sandpaper, anything like that will just rub off the paint from the surface. So after rubbing off the paint, this is the result. So as you guys can see, the copper places are there where we want. The other places has been etched away by the ferric chloride. Now legend printing. So this is basically the part where you print those characteristics, the names and stuff on the PCB. Now this is simple white paint. Nothing else here. Simple white paint and thinner. Now you can use thinner, you cannot use thinner depending on the consistency of the paint. Up to you, up to the paint that you are using. So if it's already thin enough, don't use a thinner. If it's very thick, use a thinner. It's up to you. So this is the legend. Same process. We put it under the we put it under the like the screen, and we just swipe it. Then masking. So you can use any color for the masking. We are using green here, but you can use any color. So yeah, same stuff. Mix the paint, masking paint, and thinner in 1:1 ratio. So 2 part paint, 1 part thinner. So mix it and then apply it on the PCB, and the masking will be done. Now you guys might ask that why I didn't do the legend on the top of the masking so that it gets more visible. So see, masking is more durable paint than the legend paint that the white we are using. So if we do the legend below the masking, it will give it a more durability in long term. So the masking does not, so the silk screen does not rub off. So if the silk screen rubs off and the masking is still there, the PCB is basically useless, because any XYZ person will not understand what the PCB, the holes are for, because he does not have the schematic. So that's why we do the silk screen below the masking, because the masking is the most heavy duty paint among all of this. So now, as you guys can see, it's totally ready. Our PCBs are ready. Now all you have to do is you take a small drill, not like the big drills, like a small drill bit, and then you poke a hole wherever you want to place a component. Through whole component, you poke a hole in there, and wherever you don't want to you want to place SMD component, there is no hole required. You can directly solder onto this copper patches. So yeah, this is the stuff. Now we could have done this experiment live and showed you guys, but it's lockdown and stuff like that. So I had to take this screenshots and make a you know, like a gallery and show you guys like with the screenshots, because we cannot literally perform this experiment without the chemicals, and I cannot go out buy the chemicals on a shop, and the shop is not open as well. So basically, this is it. This is the fabrication process and the stuff, like how you make a PCB, how you fabricate a PCB. Now you guys have your the discount codes in the chat, so do check them out. Now I have a small question for you guys. Do you guys know what PCB this is? Can you guys tell me what this is? Any idea? Anyone? If yes, then tell me in the chat. I want to see a comment. Any ideas, guys? Anyone from Facebook, from YouTube? What PCB this is? This is a very popular PCB. Not really a PCB printer. This is basically the PCB of the Perseverance. So this is the rover that went to Mars in 2020 and landed a few months before. So this is basically the entire main circuitry of Perseverance. This is basically the head of the rover. So this part basically goes in the main part of the Perseverance. So this is what I have been trying to show, that this PCB is not even on Earth anymore. It's on Mars at the moment. So this PCB is working on another planet, on the surface of another planet. So this is basically where the future is. Like, we are sending PCBs to outside Earth's atmosphere in vessels like this. And this is also another PCB of Perseverance. So here you can see how the PCBs are tightly packed in cases like this, aluminium housings, to protect them from dust and stuff like that. Although they are still exposed to the extreme temperatures, the whole thing is metal, so nothing is preventing from going into minus 100 degrees or something like that. Because in Mars you have extreme temperature ranges, so it has no atmosphere. So these things are still taking on huge temperature changes, but to prevent it from dust and stuff like that, it has an aluminium housing. So yeah, that pretty much concludes it. Arjita, would you like to add anything regarding the PCB manufacturing industry?
Yeah. So the thing is, we are having few more minutes in our hand. We are having like 1 hour if we want to continue. So you can actually just let them first go through different kind of PCB printing places, right? So the websites, how they can approach, they are just a walkthrough of the websites, right? Next, you can actually show them another PCB in the freezing so that they can get an idea, more clear idea. So if you're repeating and doing another project on freezing, that will be helpful for them, and we can cover up the time.
Okay. Okay. Let me do just that. Just a second. Yeah, so guys, let's see some PCB printing websites. So the first one that I would like to show is called GLC PCB. This is basically the cheapest one because they have the largest market share in the PCB development industry. So, since you know that the larger the company is, basically the cheaper they can provide the PCB because they are making in like mass batches. So, yeah, they can provide the PCBs for very cheap. So basically, this is the PCB prototyping, and they also have like their own online PCB generating tool as well. So if you want, you can directly make the PCBs from there and order from there as well. So as you guys can see, it has like technical support as well and stuff like that. So you can assemble your own parts as well. So now let's see. Here is its dimension. So basically, this means that what is the square area of your PCB? Okay. Then let's choose the quantity. Let's say I want 10 of those. Okay? So the minimum that you can take is 5 because like if you want one or two, that won't like uh, come into their like proper shipping quota because they need to ship it all the way to India, right? And then you can use one layer, two layer, four layer, and six layer. So one or two layers, and you can make at home yourself. So it does not make sense. So let's go for 4 layers. Now, thickness. So this depends on the power delivery of your PCB. So if it's a high power one, you can use select 2 millimeters. For our ones, we will just select 1 millimeter because that's a standard one. So quote now. Once you hit that, we give you a quote of your PCB. So as you guys can see, it give us an approximate shipment weight, and is asking us to give us the Gerber files. As I told you guys right that you can like send it for production if you guys produce a Gerber file. So yeah. So now it's asking delivery format. So it means that if do you want to like buy single PCB like cutout PCBs, or you want to like buy a panel, like you're buying the whole panel and then you are cutting it yourself. Okay. So you guys can see if you're taking single PCBs, that drastically reduces the price. If you want the panel, then it drastically increases the size because they have to like panels are like huge. So they contains like 20 or 30 PCBs in a panel. So basically that's why they need to ship it that big of a stuff, and that's why it's more expensive. Next is the impedance calculator. This is basically what means is that it will calculate the internal resistance of your whole PCB. So it will calculate that what is the internal resistance between the traces of your PCB. So if you do it, yes, it will charge you something, but it will like in turn do like yeah, this from this point to this point in your PCB, it will have this much resistance because the traces are in the end copper, and it's not like in practical life nothing has zero resistance, right? So everything has some minuscule amount of resistance. So this will just help you to calculate that resistance. Next is PCB color. So as you can see, by default it's green, but you can select red, you can select yellow. If you guys can see, whenever I change the color, the prices change as well because some colors are more costlier than the other ones. So all of this are like red and yellow are like $48, blue is like $31, white is like $48 again, black is 31. So basically red, yellow and white are the costliest, blue and black are the medium ones, and then green is the cheapest one at only $14. So this is basically the procedure. It will be same for almost all the places that we visit. So next, let me show you another platform. It's called EasyEDA. So it's basically an online version of Fritzing. Not exactly Fritzing, but you can say that it's online PCB design. EasyEDA. There you go. And from here you can just like design your PCB as well. So just click on EasyEDA design. You can download it as software as well, but there is no point in downloading because you can do it online. So it's more efficient that way. So as you guys can see, there is a huge library of components, but here you won't get like those graphical pictures of Arduino and stuff like that. You will only get this kind of schematic graphic logos, like figures and stuff like that. So just drag and drop it, and then you can just order your PC directly from here. So I think it's better to like go back to fritzing and then just build another circuit. So yeah, since we have built the circuit already, let's just first save it because otherwise it will just get lost. Let's save it to desktop with a name LED array. And I'm gonna save it. Okay, now it's saved. Okay, now let's make something with a smaller dimension, like Arduino Nano or something like that. In a microcircuit. So this is open. So let me close the earlier one. This is done. So I will just close it and I will place some on one side like this. Okay. Now, okay, I think there is a little bit deficiency of light. So put on some more lights. Should solve the issue. Yeah, that's all good. Okay, so let's build another one. So for this one, I'm going to take a different microcontroller so that things keep. So yeah, this is the Arduino Uno, as you can see. But I'm not going to use this one. I'm going to use this one, Arduino Nano, because it's a smaller one. And it will have a different footprint. So let me just spin it. Mm, this was- There you go. Now let's build something. LDR. Let's use LDA. So I cannot find LDA. I will search for Still loading, as you can see. So it is like a huge library. So you see, it's time to load. So as you can see, I searched the battery last time. So it already gave me some options for batteries. So right now I'm searching for relay. Let's search for so as you guys can see, it gave me quite some options. So VIP relay. So, so, okay, this is the one we want. Okay, so that's the one we want. So basically, what I am gonna build here is some automatic night light. Okay. So whenever the darkness comes on, this light will automatically turn on, okay, by itself. And whenever it's morning time, when the light has come on, it will automatically turn off. So basically, for that purpose, I am taking a relay and I'm taking this LDR. So I'm going to just place it there. Now, LDRs have two legs, right? So we need three legs for a sensor. So what I'm going to do is I'm going to make a voltage divider configuration. So let's get some more parts. There it is. Let me go to four parts. Let me take a resistance. Let me drop it right there. Okay. Now the value of this resistance is right now is basically 220 ohms. But since the resistance, higher resistance even have the same uh, kind of holes, like the size of the resistance is physically same, just the values differ by color combinations. So basically, you don't need to change it. It's originally supposed to be 1K or 10K depending on the situation, but we don't need to change it because it's good. The size is the same. 39. I'm searching for an analog pin. So it will be going further. We are going to find an analog pin. Okay, I found one. Here's a zero. Okay. Now we hold it. This right. Okay. Fantastic. Now this will go to the ground. At this ground. This ground. Now why did not I select that ground? I will tell shortly. And now we need some voltage. So let me give it the volts. Right there. Okay. Now why did not I select this ground? Because this microcontroller also needs to have some power. And I will run the power directly from that 220 volt source. Okay, focus on only that 5 volt adapter because this Arduino runs on 5 volts. Search for it. Okay, so it's basically giving an Arduino, so it does not have a 5 volt adapter. Let's try 12 volt. It's giving me nothing. Okay, never mind. So I guess we'll have to just power it with an external, like this 12 and 5 volts adapter comes in like this size of like PCBs, okay, small PCBs on there itself. So you can buy them for like anywhere between 80 and 85 rupees. So I think I need to put a space in my PCB where they can fit directly. So let's do this, just that. So I'm gonna search for pin headers. So if you guys are from electronics, you guys already know what I mean. For the rest of you guys will see it soon enough. So let's search for pin headers. So as you guys can see, I'm getting a lot of options. Yes. Okay, header 2. No, these things might look similar, but in terms of voltage, capacity, and stuff like that, it's a vastly different. So I don't know if you guys saw it or not. I went past three, like two pin headers. Is the answer simple? But I only took one because that's the voltage rating I'm choosing. Okay. So that's takes care of the low voltage side, not the high voltage side. So that will be like I think it's this one. Yeah, those are the one. So we need a lot more of this. So we need one for the source, one for the output for that, and then one for the bulk output. So good. That's all the parts we need. So I just close the parts later because we probably won't be needing that anymore. So let's just end this one. So I need this one for okay. So one of the ends are here and the other end is here. Okay. So now let's connect that to ground and let's connect that to voltage in because we can configure easily that pin what connection positive and negative is going to what pin. So that's only pretty simple. We keep it right there. So with that out of the way, now let's put the other headers. Now this will be the bulb output. So I will put it just here. Now let's see the pins of this thing. So what pin is this? Number 3. Normally open. This is the main. This is the coil. This is the coil 1, coil 2. This is main. This is normally closed. This is normally open. So for those of you who knows relay, so relay is basically a mechanical switch which is like this. Okay. So there's one port that is like this and the other port is like this. So this is normally connected when there is no power and this is normally open. So when you give power, this thing just switches from this to this like this. So now this normally closed that was previously closed when there was no power is now open. And the normally open which was previously no open when there was no power is now closed. Again if you stop the power there is a spring action that pulls the circuit back in there. So it's like this, and this. So power off, power on, and power off again. Never mind, accidents happen. So we need the bulb to glow when we send a signal to that thing. Okay. So we will be using normally open, because normally open means normally it's off. When we turn the power on, it will turn on. So we're going to use this N open and connect it to one of these things. Now we don't need to worry about polarity here, because on the side of the relay we are going to be using the AC voltage, right? So AC voltage does not have any polarity really. It's always alternating. So we don't need to worry about polarity. Now let's find the common pin. Main, coil 2 and coil 1. So this coil 2 and coil 1 is basically our output pins. So let's get some output. So I'm going to be setting it on this one, D3. I'm going to move it coil 1, okay, and then coil 2 will go to ground. So you can use this ground as well anyway. Okay, so now try to understand this. The microcontroller gives a positive signal, it energizes the coil. Now the coil moves the switch to connect the terminal, and this circuit gets connected, and then we flow alternating current through this circuit to light the bulb. Once again, when the job is done, when this time to turn off, the microcontroller goes off, like low, turns the supply to the coil off, so the coil gets disconnected, and due to the spring, it goes back. So the connection is open now, and the circuit is not closed, so the alternating current gets disrupted, and the bulb turns off. So that's the idea, I guess. So this was the switch, and then from, I guess this is the main. Yeah, that's the main. This will go to here. It's basically the place where the alternating current is entering our circuit. Okay, this will get short from here to here. So this is the other side of the alternating current that is going. Okay. Now we also need some current over here, because this is the place where which will give power to that Arduino through that converter that I was talking about. There. Now to prevent confusion, I will just pull this wire to the side, like so. There we go. So now, if I just zoom out of it, this is our whole circuit. Okay. So we have an LDR, light dependent resistor, and a voltage divider configuration. Then we have this source, and we have this alternating current source, and then we have this space where there will be a power connector, power connection board. So let me place this here, rotate this so that it's easier to understand, and then solve this rectangle over here. Okay, that's done. Now let's move over to the schematic. Now this is a very complicated project, so the schematic for this thing will be very complicated as well. Go make that stuff. I think I can say it's really, really complicated. It's intertwined with themselves. So now let's start to solve the connections one by one. So this is what we can do. So this is connected to the pins over. So those can be moved. Where is this connected to the Arduino? So it's connected in the bottom, right? There. And there. So I will just place it right there and will spin it so that, yeah, like this. Okay. Next, what I will do is I will pull up this pin. Place it there. That's simplification. Pull up this. Place it over there. As you guys can see, it's pretty simple really. Once you like, get all this tangled stuff out of the way, it's very simple. So the other end is connected with the resistance. So I will just let's put the resistance over here. So we have a ground here as well. So it will, yeah, automatically connect to the ground. You guys can see. And just rotate it. And then just go over there. And then I will just rotate this as well. And then I will just flip it so that these connections get simplified. Now over here, this will go here. Okay, so this is basically the bulb connection. Okay, so we need to make sure that it does not get confused. So we do that and we will flip it. Okay. Then we keep it there and there because these two are basically the same. They can be used interchangeably. Or we can just keep it there so that it shows that it's like a. So it shows like this is like a proper connection for that. So this is our low voltage side. So this is where the converter will connect to external circuit. It will connect here. So this is the area. This is the low voltage side, and this is the high voltage side. This is also done basically because if you like keep the high voltage and low voltage side together, the microcontroller works on a clock, right? Clock frequency, and then the high voltage side is alternating, so that interferes with the clock frequency. So to prevent that, we usually do this trick while we uh, sort out the stuff into a high voltage and a low voltage side. So here I did it as well. So as you can see, I drew an invisible I drew an invisible line over here. So this is the high voltage side over here on the right, and on the left this is the low voltage side. So now let's get to the PCB. There, there, there. So now let's check the schematic to see what was what. So basically JP3 and JP4. JP4 was the output, JP3 was the input for everything, and JP2 was the input for the the converter. So keeping that in mind, so we have to keep JP2 aside, JP1 and 2 aside. Like this, and then we just keep JP3 on one side because it's the input for everything, and then JP4 on the other side because the output for everything. Okay. And remember, we have to fit everything on top of this. So JP3 on one side, JP4 on the other side, just rotate it. This is another very tough one because we really don't have any space on the to control it. So what we have to end up doing is that we have to like rotate it or stuff like that. You can just rotate it and see. That's how we yeah, it highly simplified it. That's it. Do not control. Okay, so delete the wire. And no, that will not work. You know why? Because the this relay is a high voltage stuff on the low voltage side. So yeah, JP3 and JP4 same story as well. So these things cannot go over the microcontroller. So what we have to make is like a like a shield with an extension. Rotate it. Simplify the wiring. So,
Everyone, please shift a little bit to right side so that people can see the thing you're doing.
oh! I didn't notice at all. Sorry, my bad.
Yeah.
And then we just put the LDR. I hope now you guys can see well. Okay, so it's there. Let's see what happens. No, that made it worse. So we will keep it like this. Then we will bring it here. Let's bring this up here. So as you guys can see, this is basically trial and error, right? So you guys cannot know what will happen and stuff like that. You guys will have to just try and keep trying until that sorts itself out. We keep it here, we keep it here, and we keep checking for right there. That kinds of gives it a shield-like structure. That's something that you can do an Arduino. So it's not that close that you can influence the action of the clock. It's not that far as well. Going to provide it. We're going to use auto routing. Now, one more reason I'm going to be using auto routing is because it routes on both directions. So you don't need to worry about if it goes to the top or if it goes to the bottom. The auto routing will take care of that stuff. That is sorted. So as you can see, we have now a defined territory. So now we can do simply auto routing. Simple routing. All the conditions selecting auto routed. Just to see. Now comes the question of traces. So whatever wire we are using for like the 5-volt side, can we use the same wire for the 20-volt side because that's a lot of voltage, it's a lot of current, depending on whatever bulb you are connecting to this. So here I will suggest that you increase the trace. So how we are going to do that? We are going to go to routing. Sorry, Windows. We are going to go to inspector. So now when I pointed a wire, it shows me what width the wire is. This is basically the gauge. So it's not standard, which is 24 mil. So there's a conversion of mil to millimeters. So I will show that as well later. So this is like 24 mil. So what I want to do is for this side, whatever wires are carrying the 220 volts and stuff, let me change it to extra thick.
Maybe I don't need this much, but that does not hurt to like keep it safe. This wire as well. So it's slightly touching it there, but you cannot help it. I think I will auto route it once again to like, it's going to JP2. That's connected. That's the connector. Okay, we can leave this one standard because the Arduino won't be consuming that much of power. So that's okay. This wire also needs to be fixed up. Okay, so this is the basically the 5 volt wire is coming to the coil, and this is the coil as well. So this is basically the lamp, and this is basically the lamp. Okay, this one is to increase. So it's actually on discussion. You can basically just connect it to the this is V2. This is right into the negative. Okay, that's a fantastic. Right. So these two are the coils. In all of the other wires, what is I think the down side as well. Okay, this is a signal. Okay, so I think all of the wires are good to go. This tiny one. You cannot say that this one is good. Okay, 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 okay. This is the one connecting to there. This wire and that wire will be increased because those two are shorted out. So you need extra thick. This wire, another orange one. That's the one. You need to extra thick. All of the wires are done. So I'm going to place auto route once again, just to like maintain the space because since I have increased that distance. So as you guys can see, our PCB is ready. There is our PCB ready to go. So, yeah, auto routing is done. Everything is in order. Wow. Basically, we did not save the settings, so we have to repeat the steps. So this is why it is important to save. I didn't save it and we did not save the settings to the format. Structure. I have made all the wires except 317. Now I'm gonna go to File. I'm gonna go to Save, and I'm gonna write automatic night lamp. save it on the desktop, then run the auto routing again. Let's see what happens. Okay, so this time this one stayed. So what I am guessing from this is that fritzing won't allow me to like do this, like one all in one time. So I guess I will have to just do it manually, one at a time. So basically, I usually do my routing mine with my own hands. I don't do auto routing. So I guess that's why I didn't know about this. So if my calculations are correct. Okay, that is done basically. We got all the power hungry connections into the thick wire. So that probably won't cause any problem anymore. So yeah, that's done. So now let's do our DRC check. Designer rule check. Okay, see this wire, since I thickened this wire, this is touching there, right? That's why you gave me an error. But the relay unit is touching this place. Right? Solve it. I simply will just something like this. Okay. Now let's run another DRC check. DRC check. Okay, something is overlapping. Highlighted in red or overlapping. Okay. Something is highlighted in red and it's overlapping. So let's see. Wire 609. So let's find where this wire 609 is. This is wire 628, 623, 615, 619, 612, 624, 618. Usually highlights, but I think it's not highlighting. So 620, 607, it should be close. It says that it's overlapping, but it's not actually showing anything. So yes, it's good to go. Let me save one more time and try. Okay, still shows overlapping. Okay, so let's go auto route. That will fix everything. Is the problem. Okay, see the changes that it made right there. This was overlapping. So this should be wire 609 or something like that. Anyway, so let's do another DRC. Okay, we got other errors as well. Okay, I figured out what was wrong with this system. The system was shaking the whole thing as a flat surface, but it's not a flat surface, right? We have the front side and we have the bottom side. So basically, what happening is it's the front side is itself not like glitching. The bottom side itself is not glitching, but the DRC system is just overlapping them. So when I am seeing the front side and the bottom side differently, so you guys can see that it's not overlapping at all. So let's try doing this like this, like in a single. Yeah. See, if you look at the errors correct carefully, wire 600 is overlapping bottom layer, wire 660 is overlapping bottom layer, wire 671 is overlapping bottom layer, top layer, top layer. So this is basically detecting every single overlap in the top and the bottom layer. So that does not really matter because the top and the bottom layer is divided by the substrate. So these are just warnings, just warnings, not actual errors. So we solved our errors basically. So this is basically now ready for fabrication. So we did one more PCB. So it's really good. So as you guys can see, it really takes around only 30 minutes to design these simple PCBs. So if you guys go into more complicated stuff, it might take an hour, 2 hour. But these simple things, it really takes 30 minutes. So even less than that because I'm using this controller and I'm like facing these problems as well. So if I was speed running it, maybe I would finish it in 15 minutes or something like that. So it takes really a very small time. So now since I have time left, let me show you something else. Okay, so right now I'm opening Tinkercad. So this is basically an online prototyping platform. This is more like related to robotics and PCB designing. But the cool thing about this is you can also export the circuits over here. Okay. So for a better understanding and for a easier understanding, let me go to the same circuit. Okay. So we were building something with an LDR, right? So let me get the same circuit out because I have the LDR circuit made on here as well. So let me find that stuff and let me open that circuit. Okay, there it is. So I am not really using a bulb over here with a relay. So let me check if I have that circuit where I'm using a bulb. I mean, I could probably modify the circuit as well, but we'll just search for it. If I find it, it will be a lot easier. If I don't, I will make it anyway. Okay, it's not there. Never mind. So let's transform the circuit. Very easy, really. Let me just close the presentation. It's hogging my memory. Let me put off some note. So now the bulb is glowing. So let's understand that first. So basically, when I am decreasing the light, the bulb is glowing. When I am increasing the light, the bulb is not glowing. Okay, as simple as that. Pretty simple, really. So now what we can do is we can just remove the bulb and put a actual bulb over there. So let's bring in a relay and a bulb. I mean, this is not really related to that much PCB. This is like the designing part. But let me show you anyway, because after all, we will export it anyway. So let me show you how this thing works. And then we have a power supply because we need wall power. finally we need a relay. Single pull, single throw relay. Okay, now I'm gonna wire tile to the bulb so that you don't need to turn off the bulb, something like that. So there is basically the coil of the relay. This is around this one. So turn here. And on the other side of the coil, we should put this one. Put this one. So we'll just connect it to ground. And for my convenience, I will just color the wires. So ground goes black because that's the convention. Okay. Wiring is sorted. And then a little bit of sorting here and there. Like so. And then let's connect the bulb. So command of this thing will connect over here. Okay, on connection. So this is normally open, so this is not normally like. So this will be like another one. So this is the positive one, and then there this wire will go from there to positive. Okay, and then the negative simply go to the negative. It's colored to avoid confusion. That's done, and simply when I just turn this one, the bulb closes well. Okay, so now we have a ready ender bulb going in parallel. Okay, so for now, let me show you why this is relevant to this class. We have a substitute. So this is stuff. Now let me show you why is this relevant to this class. So if you click on export in this corner, you will get a .brd file. Okay, so we will get this brd file, and as you can see, it's downloading in this corner. So now let me open Google, type brd file viewer. Okay, so if you use this keyword like this exactly, the first thing that will have is the Altium. So Altium, as I already told you guys, is a fabulous PCB designer for industry experts, but it also has like a online board file, schematic file viewer. So I will just upload this file that I just downloaded from Tinkercad to view this file. Little bit slow, take some time. Slow it, so it should, yeah. So let me go to my downloads, like so, and there's this thing. I hit upload, process, take some time, depending on your internet speed, depending on the server load as well. So this is your, like, not exactly a PCB, but this is basically your schematic. So this is basically the, as you guys can see, this is the Arduino, and these are the components. So this not exactly accurate, and that's why we are using designers like Eagle and Fritzing. This is why we are not directly exporting this stuff from Tinkercad, because this kind of designs which are not really accurate at all. So This was basically like that thing also has that feature. Then why are we not using it? This was to just answer that question. That we have the feature, but why we are not using this? Yeah. So today's syllabus is pretty much covered. So I think yeah, we got still 20 minutes on hand. So Arjita, what do you recommend? What should we do?
Yeah, hi. So I hope everybody got a very great and very unique experience of how we can learn from live videos, and I hope it's much more interesting than boring Zoom classes. And we are trying to bring this kind of experiences for each and every technology that we are working on, from rocket science to space science, PCB to electronics to robotics, IoT, React development, Laravel development, and all this kind of technology. So, as because we are a research organization, so we work on several technologies to actually do things. Uh, that can actually help people to solve problems. Maybe that's a individual problem, or it's a community based problem, or a business problem, right? So we help people to build their products, their software products, hardware products. So what we are doing, we are actually trying that, as because right now the colleges are not open, schools are not open, and somehow people are not getting hands-on training, right? So even if they are going to the college, they can use the labs, but that is not possible at this point of time. So it's a very point of scarcity and very diversified time, dicey time. So we are trying to create another kind of experience through which, so you can understand, if a live class, live free demo class can be like this, what we provide in paid classes, paid workshops, right? So that's how we are trying to actually change how we actually learn things, right? So that's what we are trying to do. So this kind of sessions will happen on every Sunday. So you can go to Facebook page of Think Again Lab, facebook.com/Think Again Lab. So you can go and check out all the other events that we are hosting. Even we are including stock market classes, entrepreneurship classes. So it's a 360-degree learning experience, and you don't need to pay a single penny. Even you are getting scholarships that you have seen today, that we are actually providing scholarship on the spot. So the person who owned the 100% scholarship, he already registered himself for the class, right? He got the scholarship code and registered. So it's not fake, it's not vague, it's absolutely transparent and true. And that what I have said, that if you can answer 10 right questions, you will get 100% scholarship, and one person got 100% scholarship, and 60%, 40%, 20% other people got this kind of scholarship. So congratulations to all of them, and hope I can see all of you in the class, in the master class. And all the best to your endeavors. And one thing we are doing for you, for the community, for the youth community. So we just want one thing in return, that talk to your friends, let them know that we are doing this kind of thing. Because if people are not aware of this kind of live free sessions, then it is of no use to do these things, because we are not earning a single penny from it. We are doing it just to let you understand what kind of industrial careers are there, how you can actually pursue those careers, where to start things. And those people who are actually, so as because it's a live class, anybody can go to our pages, the youtube channel, or different places, and see the things, comment down things. But those people who are actually registering prior to the event, registering for the event, they are getting the certificate, they are getting the 70% direct scholarship, they are getting several other scholarship for our hands-on long-term courses, as well as they are actually they are getting different access to our groups, our channels, our Slack channel, WhatsApp channel, so that they can actually get connected with the experts and solve the problems they are facing throughout their career, related to CV making, related to choosing a company, how to get an internship, how to learn PCB design if you're stuck somewhere. So it's a 360-degree learning experience we are trying to provide. So I would love to request everybody that as you are watching this thing and you are interested about it, because 3 hours is a long amount of time, and 4, 5, 6 people are continuously commenting, and several hundreds of people are watching the live show, and I hope people will watch it later on as well, because we are going to upload these things on YouTube, Facebook, and all those places. So go to Facebook page or Think Again Lab website and register for the other sessions, like we are having React.js, graphics classes, digital media marketing, share market classes. So go and register, like our page, join Think Again Lab community group, because we used to share lots of rocket science related, space related, robotics related things in our groups. So join that group, and all the best for your future. Thank you so much, Anirban. Hope
Thank you.
people liked your session, and we have to take feedback from them so that we can actually make it more better. Thank you so much for a lovely class. Thank you so much. Good night, everybody. See you on next Sunday.